Right, so thank you very much, Giulio and Panagiotis, for your kind invitation. So this webinar witnesses that the importance of batteries for present day and next generation technology can hardly be overemphasized, because the option of powering electrically and independently a range of devices, for transportation in particular, has received notable impulse from the introduction of lightweight, high voltage lithium-ion technologies that enabled, as I'm showing on the left side of these slides, a leap forward, a factor of about 5 in terms of volumetric and gravimetric energy and power densities with respect to traditional systems essentially based on heavy lead, nickel, and cadmium. And battery production and use have exploded over the last decade, and their prospects for near future are those of a steady increase with a growing proportion of transportation applications, as shown on the graph on the right side of this slide. So the ambition of this talk is to outline this immense field by proposing a simple description of the principles of battery operation that will lead to a basic understanding of the role and interaction of battery components that are implemented in a range of chemistries and technologies, calling for progressively better understanding of the properties, mutual influences, and issues. And in the second part of the talk, I will briefly sketch the way optical spectroscopies and microspectroscopies are contributing and can extend their contribution to gaining a better insight into battery materials. So talking about batteries means talking about electrochemical processes in which electrical and chemical works are coupled. Specifically, batteries implement redox reactions in which reduction and oxidation processes are kept separated in space. Concretely, to fix ideas, let's concentrate on a prototypical redox reaction, namely hydrogen combustion with oxygen, whereby hydrogen is oxidized and oxygen reduced, and the electrical counterpart of hydrogen oxidation and oxygen reduction is electron transfer from hydrogen to oxygen atoms. So in an admittedly crude but perhaps effective scheme, this redox reaction can be carried out in a homogeneous way, say in a flame, in which the reagents are mixed and electron transfer takes place within the activated complex. Alternatively, the individual reagents can be fed to different regions of some sort of device where they are separately reduced and oxidized. So the redox reaction is completed by bringing together from the ox. Can you see my pointer? From the ox to the red sides. On the one, electrons through some electronic conductor, and on the other hand, the respective reaction products. Since reaction products are typically ionic in form, they can be brought together by some ionic conductor. So a redox reaction running in the electrochemical way, alias with spatially separated red and ox sides, can thus be described in electrical terms by means of a loop, consisting of an electronic and an ionic branch, the latter called electrolyte, joined by 2 points at which electronic charge carriers are exchanged for ionic ones. Again, these are spatially separated, these occur as spatially separated red and ox reactions, the sites of which take on respectively the names of cathode and anode. The battery can thus be regarded as the part of the loop that comprises all that is different from the electronic conductor, which of course represents the load of the battery charger. The details of red and ox reaction rates, mass transport, and ionic conductivity yield the nonlinear EV characteristic of the battery. And material evolution connected to the progress of the chemical reaction, coupled to electrical phenomena and irreversible material changes, bring about the typical time dependence of the battery IV. So this general scheme can be implemented in a plethora of ways, which represents the wide range of available and prospective battery chemistries and technologies. The anodically and cathodically reacting materials can be in any physical form. You can find gases, liquids, and solids used in different battery technologies. But here, for the sake of simplicity, we shall stick to the more common solid ones. Now, a crucial aspect of solid reactions that run at solid electrodes is that they can occur without or with accompanying phase formation processes. We refer to intercalation electrodes, which are the ones that Akshay has talked about in the former case, and conversion ones in the latter. Conversion electrodes will be implemented in next generation lithium battery technologies and in future post-lithium technologies. So now, referring to the specific case of lithium-ion batteries, but the processes are very similar also with other chemistries. During battery discharge, intercalation cathodes undergo reduction by incorporating lithium ions into hollow crystal sites of different dimensionalities, simultaneously taking up electrons from the external circuit that reduce some element of the host structure. So in this scheme, for example, I'm showing ion 3 reducing to ion 2. This is a case which schematizes the reduction of lithium iron phosphate cathodes, thus preserving electroneutrality. Now, during battery recharge, the process is simply reversed. Intercalation anodes instead work in a similar way, with the difference that here lithium is directly oxidized during the intercalation and reduced during intercalation, rather than having a redox which is mediated by reduction or oxidation of some of the host materials. Now, intercalation electrodes are desirable because since they do not undergo a phase change during, a phase formation process during redox, they bear promise of dimensional stability during cycling. But the downside of intercalation electrodes is that, being based on host structures, they exhibit an intrinsically low density of active material. Now, this drawback can be circumvented by using conversion electrodes, which merely consist of active material, though at the cost of phase formation processes in correspondence of each discharge and charge half cycle. Well, these phase formation processes generally lead to shape changes of the material, of the active material, that are presently poorly understood and controlled, and can lead, on the one hand, to the detachment of active material from the electrode, causing capacity loss, or the formation of dendrites liable to give rise to internal short circuits. Regarding electrolytes, a wide range of materials can be employed, the most common of which are porous membranes soaked in solvents with dissolved ion salts, gels, in which essentially the same solution is incorporated within a polymeric framework, ionically conducting ceramics for the famous solid-state batteries, and ionomers. Now, a classical way, though not the only one, of assembling electrodes and the electrolyte into a battery is to fabricate the active materials, like the one Akshay has shown, in the form of powders, and to prepare slurries based on these powders, and to spread these slurries onto metallic foils acting as current collectors. The electrolyte, again in the form of a foil, is interposed between the two electrodes that are typically rolled or stacked, forming a unit cell. Modules and packs, which are the objects that we actually see when we look at a battery, are assembled by connecting an appropriate number of single cells in series or in parallel. Now, from what we have seen so far, it is evident that the battery is a multi-material system with a complex multi-scale architecture ranging from the millimeters to the nanometers, more or less as Akshay has pointed out, operating as a transient state, exhibiting reversible and irreversible dynamics on a wide range of time scales that, again, Akshay has indicated, hours or many hours, days, to milliseconds if we think about electrochemical kinetics, but indeed lower if charge transfer acts have to be accounted for. Now, gaining insight into the properties and operation of these devices calls for capabilities of looking inside them, and this is precisely the task of inoperando spectroelectrochemistry. Now, in the rest of the talk, I shall briefly give some examples of the way optical spectroscopies can be used for the purpose of following the behavior of battery electrodes and electrolytes. So starting from intercalation electrodes, in situ visible UV spectroscopy in reflection was found to be responsive to lithium insertion and extraction into and from carbon-based electrodes. The absorption spectrum changes as a function of the degree of intercalation, and the optical response of the anodic material, for example, measured with an optical fiber inserted into the anodic active layer, allows to quantify the state of charge of the electrode. And so with a similar optical fiber-based approach, placing the optical fiber in the cathodic active layer of the material, the visible spectral response of the cathode material, in the case of this example, this is again lithium iron phosphate, the lithium iron phosphate cathode. So the optical response of the cathode material as a function of the degree of charge or discharge can be employed to monitor the degree of charging of the electrode, so the amount, essentially the amount of charge that has been stored at a given depth of discharge. Now, in situ Raman, typically performed with one-sided cells, has been extensively employed to follow the structural changes that accompany lithium intercalation in a range of graphite-based anodic materials, as you can see an example on the left panel of this slide, or of oxide and phosphate-based cathodic materials, an instance of which is reported on the right of this slide. Raman spectroscopy allows, in a simple and straightforward way, which also allows the implementation of the optics in a way whereby the really active material of the cell can be sampled. So it allows to detect deviations from the nominal structural reversibility of intercalation systems brought about by electrochemical cycling. Moreover, Raman mapping can disclose the space distribution of the intercalation degree in the composite electrode layer, helping prospectively to optimize electrofabrication and discharge policies. One of the safety problems experienced with some innovative high energy density oxide-based cathode materials, like the high nickel cathodes that implicitly Akshay was mentioning, is that upon delithiation, unstable crystalline forms can develop, liable to release oxygen. Now, in situ Raman has been used to address the safety relevant oxygen stability issue through the detection of peroxide formation during electrochemical polarization. So in given potential ranges, in given ranges of the depth of discharge, this incipient form of oxygen reduction has been detected. Now, regarding the interaction of electrodes with the electrolyte phase, visible infrared some frequency generation spectroscopy employing internal reflection cells allowed to measure the absorption of solvent molecules at the surface of intercalation electrodes, highlighting, among other aspects, in particular for the case of mixed solvents, whereby different types of organic materials are mixed in order to optimize the functional performance of the liquid phase contained in the battery. So in the case of mixed solvents, it has been shown by spectroscopy that the relative surface coverage is typically different from the relative bulk concentration, indicating some sort of preferential absorption. And this has a bearing on electrolyte decomposition and formation of interfacial layers, which strongly influence the battery performance and durability. Now, as far as conversion electrodes are concerned, in situ visible light microscopy with transverse visualization cells allowed to follow mesoscopic changes in shape as a function of time and operating condition. And this straightforward morphological information can be effectively combined with electrochemical data to yield a quantitative description of cell voltage response based on parametric models in view of monitoring and control. Now, that, coming closer to what Akshay was saying in the previous talk, the dynamic lithium-ion concentration distribution is known to affect unstable growth of metallic lithium. And on this slide, I'm showing some examples of computational estimates of this effect. But lithium-ion concentration is a quantity which is really hard to measure, but thanks to the high chemical sensitivity and imaging rate capability of stimulated Raman scattering microscopies, it was possible to map this quantity in 3D through the mediation of a reporter molecule, in fact, the counter anion of the lithium salt, which has been used. And it was possible, in particular, to map the three-dimensional time-dependent concentration distribution of lithium ion during the dendritic growth of lithium. In this way, the postulated lithium depletion layer forming in the proximity of growth features, which I marked with a blue arrow, could be positively assessed, paving the way to the control phenomenon by chemical and electrochemical means. One way to suppress dendritic growth is electrolyte modification additives. These additives are believed to absorb selectively at outgrowth features, and in situ Raman spectroscopy allowed to follow potential dependent reactivity and absorption of additive molecules that correlate with smoothing of plated metals. And in some cases, it was found that the reaction products, the electrochemical reaction products, are in fact the effective species giving rise to the smoothing effect. While the limited surface sensitivity of non-SERS active electrode surfaces calls for vibrational spectroscopies with intrinsic surface sensitivity and capability of resolving surface orientations. Now, in situ, visible infrared SFG, employing external reflection cells, is an appropriate option that allow to follow the in situ formation of adsorbable reaction products and to discriminate the species that tend to absorb at different potentials that in turn can be correlated with the electrode morphology distribution. Of course, SFG microscopy, that does not seem to have been described so far, would allow to positively assess the localization of absorption. Now, regarding the last cell component, namely the electrolyte, a crucial issue is the determination of the coordination of lithium ions by solvent molecules. Raman with reflection cells and FTIR with transmission cells allowed to detect the vibrational signature of the coordinating solvent, the relative intensity of which can be used to monitor potential dependent lithium salt concentration, as in the case of the Raman measurements reported on the left of this slide, or to estimate the lithium coordination number with the FTRS spectra that I'm showing on the right side of the slide, obtained by varying the lithium salt concentration. Dynamic infrared measurements enable a deeper understanding of lithium coordination, addressing the interaction of the coordinating solvent molecules with the solvent ambient. In particular, polarization-sensitive IR pump probe spectroscopy disclosed that the vibrational lifetimes are sensitive to ion coordination, and two-dimensional IR spectroscopy revealed the progressive formation of crossed peaks corresponding to solvating molecules, denoting energy transfer from solvent molecules outside the lithium ion solvation sheath to solvating ones. This rich structural information regarding the electrolyte phase will have to be linked with the functionally relevant reactive absorption and charge transfer processes undergone by the coordinating molecules and the coordinated electroactive ion. Moving now from liquid to gel electrolytes, FTIR microscopy, by mapping at appropriate combinations of vibrational frequencies, allowed to map crystalline and amorphous domains of the pure polymeric framework and to quantify pore filling by the lithium-containing solution. Similarly, CARS microscopy enabled mapping the solvent distribution in the three-dimensional structure of the polymer framework. And this information and its extension to in situ applications can be directly linked, on the one hand, with the effective ionic conductivity and mass transport of electroactive species, and on the other hand, with the morphochemical stability of the composite electrolyte and electrode-electrolyte interfaces. Now, before concluding, I only mention in passing X-ray methods that can convey crystal structure, chemical state, and electronic structure information with multi-scale imaging capabilities in the direct and Fourier spaces. Well, these techniques would deserve, of course, a separate treatment. And in conclusion, I should like to propose some general and prospective comments regarding the use of optical spectroscopies for the study of battery materials. First of all, the direct bearing of optical studies on battery technologies should be increased by moving beyond the proof of principle stage and targeting functional monitoring, providing concrete guidelines, among others, for the assessment of battery state, exploiting explicit material information. Monitoring control beyond merely electrical and thermal, which is the state of the art, understanding of degradation, as Akshay was pointing out in the previous talk, and then routing spent batteries to dedicated and environmentally friendly and sustainable recovery processes. Secondly, the realism of in situ and inoperant experiments should be increased with advanced cell design, targeting especially current density distribution issues. Moreover, interoperable sample ambients should be developed, enabling multi-technique studies under identical electrochemical operating conditions. And in addition, nonlinear methods ought to be more intensively adapted to the study of electrode materials. And finally, I should like to call your attention to the fact that training young scientists with experimental skills crossing the border between electrochemistry and spectroscopy will probably be more and more scientifically rewarding in the near future. And thank you very much for your attention.
Thank you very much, Benedetto, for this really nice and comprehensive presentation.